Welcome. In this explainer, we're diving into what is, honestly, one of the most fascinating ideas bubbling up in tech and science right now. And that's the deep, almost uncanny similarity between large language models and actual living biological systems. You'll see this goes way, way beyond just a simple metaphor. So let's just kick things off with a big question, something to frame this whole conversation. I mean, on the surface, these two things seem like they're from different universes, right? One is wet, messy, evolved over billions of years. The other is silicon, code, trained in maybe a matter of months. But what if they're both just different answers to the exact same ancient question? And this is that fundamental question. You could say it's the core problem that any intelligent system has to solve. Doesn't matter if it's grown in a lab or built in a data center. The problem is, how do you take all of your past experience, compress it down into some kind of useful structure, and then use that structure to make good decisions when you have no idea what's coming next? So let's break down how each of them tries to pull this off. Okay, so first up, we're going to explore how facing this shared problem basically forces both biology and AI down these surprisingly similar paths. And it's not magic or anything. Well, you can think of it like a kind of convergent evolution, but for processing information. So here's the side-by-side. Biology's compression algorithm is, evolution and learning. It stores the results in our DNA, our brains, our entire bodies. LLMs? They do pretty much the same thing, except their experience is a giant data set, and their body is this incredibly intricate network of weights and parameters inside the model. At the end of the day, both are creating a compact set of instructions for what to do next. And because they're solving the same problem under really similar pressures, like the need to be efficient, they end up using the same playbook. It's amazing. They both build things in hierarchies, from simple to complex. They both use specialized modules for different jobs. And this is a huge one, they are both totally shaped by their energy budgets. These are not just coincidences. These are strategies that have been battle-tested for dealing with a complex world. All right, now let's dig into how this shared problem leads to some truly striking parallels in their actual design. This is where the analogy gets really concrete and, to be honest, a little bit mind-bending. So, at the very heart of both systems is a process of selection. Evolution, that's a slow, methodical filter, right? What works well enough gets to reproduce. Well, training in AI is just a hyper-speed version of the exact same idea. Instead of reproductive success, the filter is predictive performance. Does the model get closer to the right answer? If it does, great, its parameters get reinforced. If not, they get tweaked. Both are just these relentless optimization engines. And what actually gets stored from all that trial and error? Here's the key. It's not a list of facts. It's a set of rules and constraints. Think about it. Your DNA doesn't have a perfect blueprint of an eyeball just sitting there. It has the rules for how to build one. In the same way, an LLM's weights don't contain a bunch of pre-written sentences. They contain the deep grammatical and semantic constraints that shape how a coherent sentence can unfold from a simple prompt. Ooh, this one is just beautiful. So both systems have a slow, stable, hard-to-change memory. That's DNA for us, and the core weights for the model. But they also need a way to adapt really quickly without rewriting everything from scratch. So how do they do it? In biology, we've got epigenetics. These little temporary chemical tags that turn genes on or off depending on the environment. And in LLMs, it's the context window. It acts as a temporary regulatory field that tells the model how to behave right now for this conversation without permanently changing its core programming. It's the same design pattern. So the crucial point here is that this isn't some mystical, spooky connection. It's almost mathematical. When you have a process of selection that's acting on a system defined by a set of constraints, and you add a little bit of noise or randomness into the mix for exploration, you just tend to get similar designs. It's like a universal recipe for creating complex adaptive systems. Now, what's really, really interesting is when you lay out the memory stack like this, to be smart and useful in the real world, you can't just have one type of memory. It turns out both biology and AI have figured this out. They layer their memory by timescale. You have the really slow, deep-seated memory, our genes from evolution, or the model's pre-training data. Then you go all the way up to the fast, temporary working memory of our thoughts, or the LLM's context window. And you even have external memory, like us using books or tools, and an LLM using a database with RAG. It's an entire memory hierarchy. Okay, But a good analogy has to know its limits, right? So to be intellectually honest about this, we have to be super clear about where this comparison completely breaks down. Because trust me, the differences are just as important as the similarities. And this is probably the biggest difference of all: grounding. A living thing's model of the world is constantly being stress tested by physical reality. If it's wrong, there are real consequences: pain, hunger, maybe even death. An LLM, though? It's only grounded in the data it was trained on. For an LLM, being wrong just means it failed to predict the next word correctly. It has absolutely no skin in the game. And flowing right from that, organisms have goals that are built in. A squirrel doesn't need to be told to go find nuts. That drive is intrinsic. It's part of its programming. An LMM has zero desires, no drives, no intentions of its own. It's a tool, and it only pursues the goals that we give it through a prompt. That's it. And finally, there's embodiment. Our intelligence is so profoundly shaped by the fact that we have a body. Our understanding of simple concepts like heavy or smooth comes from direct physical sensory experience. Today's LLMs are basically pure disembodied minds. They only experience the world through the proxy of text, which is a massive limitation on their frame of reference. So, now that we've looked at the incredible parallels and the really crucial differences, let's bring it all back together and actually state the core thesis here, the big, powerful idea that this whole comparison reveals. And this quote just nails it perfectly. We have to stop thinking of these systems as databases full of facts. They are constraint machines. Their knowledge isn't a list of things they know. It's a finely tuned geometry of tendencies. It's like a landscape of possibilities, a giant map of relationships and concepts that only collapses into a specific behavior when a context, like a real-world situation or a user's prompt, arrives. So let's just quickly recap the big takeaways. First, both systems store constraints, not prepackaged answers. Second, they both use context to generate new emergent behavior that wasn't explicitly programmed into them. Third, they use randomness not as a bug, but as a feature, a way to creatively search for solutions. And finally, both are fundamentally shaped by the inescapable laws of thermodynamics. Their energy budget, whether that's metabolism or compute power, dictates their entire design. And that just leaves us with one final, absolutely massive question to chew on. If these forces, selection, constraint, and energy, are truly the universal principles for building any kind of intelligence, then it suggests we're not just inventing AI, we might actually be discovering something fundamental about how information organizes itself into intelligent systems, no matter where they pop up in the universe. So what does that mean for what we build next? Now that is something to think about.